All right, we begin our pre-recorded lectures for this semester with Chapter 1. And as we go through Chapter 1, the goal is for everything to seem familiar, right? Because as you can see, Chapter 1 is all about remembering general chemistry, specifically the key parts that are going to be important to set the foundation for the rest of this semester. Right? Atoms and molecules, of course, electronic structure and bonding, of course, but also MO theory, molecular orbital theory. That's a big one we covered in Chapter 8 in Gen Chem 1. We touched on it a little bit further the second semester, but MO theory is going to come back with a vengeance here this semester. So that can be a little tricky when you first learn it. We'll continue to use it in organic. But circling back, right, you want everything to seem familiar. If you're going through Chapter 1 and any of these ideas, you're like, oh, I totally forgot about that, or wow, I really struggled with that when I took Gen Chem. My recommendation would be that you go back and revisit these topics, right? Bust out your old Gen Chem textbook or look up some extra resources online and make sure that you are really strong in all of these subjects, because then you're setting yourself up for success as you proceed through the course, right? And as you do your homework on sapling, that'll be another opportunity to identify any areas where you might have some weakness. Okay. So for this first video, I'm going to cover 1.1 through 1.3. We'll call that section 1 of chapter 1. Probably looking like about 5 videos or so for chapter 1, 5 or 6 videos to keep your eyes out for. Okay. First question, you're in the course, right? What is organic chemistry? And depending on who you ask and how old they are, you might get a different answer, right? And effectively, what it used to be was that organic was the study of compounds that came from a living system, right? And inorganic was everything else. But that definition kind of fell by the wayside, right, when urea was synthesized from ammonium cyanate, right? Because urea, right, is found in your body, and it came from something that was inorganic. So now the line was kind of blurred between the two. So the loose definition that you'll get from anyone, what is organic, right? Just things that contain carbon. If it doesn't contain carbon, we tend to lump it in with inorganic. So the next logical question, okay, I'm in the course, I know what organic is. Why is that important? Well, if we think back to organic being the study of things found in living systems, right? Everything that makes life possible is an organic compound. Everything that keeps your body running day in and day out, no matter how much abuse you put on it, right? That's an organic compound. Okay. The field of organic chemistry also deals largely with natural products, right? Finding things from nature and then making them via synthesis. And then, of course, there are a whole bunch of things that aren't found in nature that are synthesized as well. Okay, if you go and get a master's or a PhD in organic chemistry, chances are you're working to some degree in synthetic organic chemistry, making new, novel things. Okay, and to date, there are 16 million unique organic compounds, and that's growing every day with things being discovered, isolated, etc. And why is that field so big, right? Just thinking about the study of carbon. Well, think back to electronegativity, right? We talked about that general trend in the past of electronegativity. The increase is going up and to the right, excluding the noble gases. But carbon's kind of in the middle. It doesn't readily give up electrons like things in group 1 or 2, and it doesn't necessarily readily take up electrons either, like group 17 or 16. Carbon likes to share electrons. It forms covalent bonds really well. So it gives it this unique field of study. Okay, it's in the middle, it shares, forms 4 bonds. That's old news. So what are we going to study this semester if we had to make it as succinct as possible? Right, we'll study how organic compounds react, right? And that's what makes organic difficult for some, and that's what gives it the reputation, right? It's not just, okay, I've got these reactants, what products do they make? You have to know the how and the why of why these reactions are occurring, okay? So we'll talk about those covalent bonds and how they break and then they form again and how easy it is to do that, thinking about reaction energies. And we're always going to be tracking electrons, how individual electrons or pairs of electrons move throughout what's known as a reaction mechanism to get that reaction from point A to point B and sometimes point C, D, E. Okay. And then the one other thing that I'll talk about now, we'll see it come back with a vengeance in chapter 4, is the other difficult thing is seeing things in 3D. Okay. So that's where you'll need a model kit to visualize these things, because you have to picture them not just on paper anymore, but in 3 dimensions. So getting into topics that should seem familiar, right? Structure of an atom, okay? You know what an atom has. It has protons, it has neutrons, it has electrons. We don't have to get any smaller than that, worry about things like quarks or bosons or anything like that. You should know that protons are positively charged, neutrons are neutral, right? No charge, electrons are negatively charged. That's old business. The atomic number corresponds to the number of protons. Okay? So take the atomic number of carbon. Atomic number 6 has 6 protons. Okay? How do we figure out the number of neutrons? Take the atomic mass, subtract the atomic number, right? A minus C. So I went through that fast because I'm hoping if you made it to this level, all of that is, you could do that with your eyes closed. Keeping in mind also the mass of these things, right? So electrons weigh about 1,800 times less than do protons and neutrons, right? So most of the mass is in the nucleus with the protons and the neutrons, but the volume of these things is in the electron cloud. And that electron cloud is actually where we're going to focus this in most of next semester, because that electron cloud controls how bonds are formed, moving electrons around. Also remember isotopes. Okay. That's old news as well. Those numbers for the atomic mass on the periodic table, those are a weighted average of all isotopes. Okay. So what is an isotope? Same atomic number, same number of protons, right? But a differing number of neutrons, therefore a different mass number. Okay. So here we say see 3 different isotopes of carbon. So that's all. Structure of an atom, isotopes. That's 1.1. If any of this is unfamiliar, right, go back and review that material. And as always, with any of this stuff, shoot me an email with questions or post them on Blackboard. So let's look at 1.2 now, distribution of electrons in an atom. This is tying into our General Chemistry 1, Chapter 6. This is where we first started to see this idea, right? We have these shells where our electrons fill in, and we talked about quantum mechanics and motions of electrons around the nucleus and the discussion of electrons being both a particle and a wave. Schrodinger, all that work. Okay? But in this course, the good news is we're largely only concerned with the first 2 shells, because that's where carbon is. Okay? So we'll be working with, right, the 1s, the 2s, the 2p, and to a lesser degree, the 3s, the 3p, and not really any of the 3d or beyond that until next semester. Okay, so we've got that first shell, right, the s orbital. Right? It can hold 2 electrons. That's hydrogen and helium for the 1s if we're looking at the periodic table method. And we've got the second shell, the s and the p, where you can hold 8 electrons. Right? Keeping in mind that each individual shell only holds 2 electrons, each individual subshell, right? So you've got the px, the py, and the pz, those dumbbell-shaped things that are all pointing 3 different ways, right? So 6 in the p, 2 in the s, 8 total electrons in the second shell. As those numbers go up, we're getting further away from the nucleus and higher in energy. And again, I'm hoping all of this sounds familiar. Okay, recalling old material. We're going to be thinking about ground state electron configurations to start. That's where we put all of our electrons in the lowest energy atomic orbitals, right? So that's the ground state, not to be confused with the excited state when we've promoted electrons to higher energy. We have the Aufbau principle that controls our ground state, right? We're going to the lowest energy possible when we fill it up. Pauli exclusion, I just talked about, right? No more than 2, because we can't have any electron with the same set of 4 quantum numbers. Right? Don't forget those 4 quantum numbers as well. And then Hund's rule as well, which we'll discuss a little bit. Think about like if I'm filling the p orbital, I'm going to take each individual unoccupied before I start to pair up, right? So if I'm filling the 2p, for example, it'd be spin up, spin up, spin up, then spin down, spin down, spin down. All of this hopefully sounds familiar from chapter 6. If not, go back and check your notes. Okay, that should come back rather quickly because we continue to discuss those ideas in later chapters. I've also used these terms, and we will be talking about them a lot, right? Valence electrons and core electrons. Valence electrons are those in the outermost shell, and those are what we're concerned with in organic because that's what controls bonding, right? Where those electrons are in the valence shell. The core electrons are everything inside, okay? And as we recall from chapter 7 in general chemistry, bonds form in order to create octets in the valence shell. It's got the rule of 8, and we know there are some exceptions to that, but just general bonding principles that are covered in 1.2. How about 1.3? Oh, and except hydrogen, right? Octet rule, but we know hydrogen's happy with just a pair of electrons because then it's isoelectronic with helium, which is, of course, the whole point of the octet rule, to make it isoelectronic with a noble gas. So finishing up with 1.3, okay, that discussion of valence electrons in the octet rule. Okay. Atom is most stable if it contains 8 electrons. So we can do that by losing an electron. Things in group 1 and group 2 like to lose electrons because then they become isoelectronic with the previous noble gas, right? Lithium's not going to gain 7 more electrons when it's starting with 1. It just loses that electron and then goes back and becomes isoelectronic with helium. Okay. Sodium, same thing, becomes isoelectronic, right, with neon. But if we look at it the other way, right, group 17, fluorine and chlorine, they have 7, they're going to gain an electron to become isoelectronic with a noble gas. Okay. And that, again, relates to our concepts that we discussed in chapter 6, right? In chapter 7 in general chemistry, electronegativity, okay, ionization energy, electron affinity in those periodic trends. That's why these things behave in that manner and have, you know, high electron affinity or low ionization energy, because they want to achieve these energetic minimums, which really is what organic all boils down to. Okay. Hydrogen can do one of 2 things, starting with 1, right? It can lose an electron, become a proton, have an empty outer shell. That's largely what we'll be dealing with in first semester organic, right? Hydrogen and protons. But a hydrogen atom can also gain an electron, become isoelectronic with helium that way. That's known as the hydride ion, H-. Okay? And we'll see that a lot in organic too, but we just put it on the mental shelf for now. Okay. We've already talked about achieving the octet, right? We know we can do that with ions as we just saw, but organic's going to be all about doing it via covalent bonds. That's the huge part of organic chemistry. Share a pair of electrons, it counts towards both atoms in the bond. They can form an octet that way. We see it doing with diatomic fluorine here, diatomic hydrogen down here. And remember the difference between the lines representing bonds and the dots representing lone pairs, of course. I kind of glossed over that, but make sure you know how you're counting all of the electrons in these bonds. Okay. Doesn't have to be the same thing, right? We know these would be nonpolar bonds because it's the same atom in the bond. But here, right, 2 different atomic species forming a bond, but it makes both of them isoelectronic with a noble gas. Okay. Here, however, different bond, because hydrogen and chlorine, that's going to be forming a polar bond versus when we had nonpolar before. Okay. And we can form a variety of different bonds. I said several minutes ago that carbon likes to form 4 bonds. Nitrogen likes to have 3 in a lone pair. Oxygen likes to have 2 bonds in 2 lone pairs. And that ties back to another idea from general chemistry known as formal charge, right? In each one of these situations, that center atom would have a formal charge of 0, versus if I did oxygen with 4 bonds for example, you'll never see that. That would have a formal charge of +2, be much less stable. Already talked about polar and nonpolar bonds, right? Corresponds to that difference in electronegativity, right? The greater the difference in electronegativity, the more polar a bond is. Okay. Which should be pretty similar, right? We talked about these trends already. You will not have to know these exact ideas, right? We'll be dealing with largely nonpolar covalent bonds to start, and then see how the change in polarity affects the reactivity. Okay, but if it's got a difference of electronegativity 0.5, 0.6 or less, right, that's typically nonpolar. In the middle, 0.5 to 1.9, that's a polar covalent bond. And then above 1.9, it's too much of a difference. It's no longer going to be shared, but rather just transfer the electron completely and form an ionic compound rather than a covalent compound. And those ionic compounds then are held together by electrostatic forces, not shared electrons. When we have a polar molecule, we also have a dipole moment, right? Because we need to be concerned not just is a bond polar, but is the molecule polar as well. So our bonds will have dipoles, but then we also need to consider the compound as a whole in its geometry, okay? Because just because we have a polar bond doesn't necessarily mean we have a polar molecule, okay? Something like carbon tetrachloride, 4 polar bonds, but non-polar overall. So that's another key idea from those early chapters, 6, 7, and 8, to pay attention to, right? These electrostatic potential maps. Do I have something non-polar or do I have something polar? Because those will have vastly different reactivities, and that'll be important quickly when we talk about the context of acids and bases. The last other thing that's useful for these electrostatic potential maps is they do give you a rough idea of the size distribution. Okay. So that concludes this first part of chapter 1, 1.1 through 1.3. We will pick up the next video with chapter 1 starting in section 1.4.